Hi everybody, today we are going to be starting a new unit on kinetics, and so let's just dive right in. All right, hang on a sec, let's see. I don't want to write with red. Okay, so you've probably heard the word kinetics or like kinetic energy in some science class before. So kinetic energy we think of as the energy of motion, whereas potential energy is the energy of position. So kinetics in chemistry is almost the same thing. It is like the energy of motion, except that we're talking about chemical equations. So chemical kinetics is really the study of the motion of molecules in a chemical reaction. And so I'm going to call that the speed of chemical reactions. Chemical kinetics is the study of the speed of chemical reactions. So there's another word that we use for speed in science, and that's the word rate. Rate is the word that we are going to be using for the whole rest of this time together. And I will do my very best to always make the connection that speed and rate are the same thing. They mean the same thing. They're just two different words. But we are going to be using rate. Okay, so there are a couple of different things that we have to keep in mind. In our chemical reaction, we have reactants on the left, and those combine and react to form products on the right. So the rate of a reaction is equal to triangle, and I'll explain what triangle means. So I'm going to write all this down first and then I'll explain it. Triangle concentration, oops, it helps if you can spell, divided by triangle small t. Okay, so do you remember what triangle stands for? Hopefully some of you do. Triangle is the Greek letter delta. Can you see that? Nope, not at all. Let's see. Let's try the yellow. It's a little bit better. Triangle is Greek letter delta, and it always means change in. So whenever you see triangle, don't think triangle, think delta. And you can think of it as like meaning the words change in. So here we have change in concentration minus the change in small t, which means time. The way that we calculate delta, or that change in term, is always going to be final. So we'll find the final concentration of our reactant minus the initial concentration divided by the change in time. So final time minus initial time. This is a lot of words. If you have to pause it to catch up in your taking of notes, go ahead and do that. As a reaction progresses, two things happen. The first thing is that reactants are used up. So if we're thinking about our regular explanation or our example of a chemical reaction, if we think about building a sandwich, the reactants are used up. The reactants are the ingredients. So you're using up pieces of bread and pieces of cheese and pieces of meat, and you are making products. So what does this mean in terms of concentration? The concentration of reactants will decrease over the time of your reaction, and the concentration of your products will increase. I'm going to write that down for you. Concentrations decrease for reactants. And concentrations increase for products. Okay, so that's not really anything too special or new. Dang it. I hate how it does that. Let's try doing this. Okay, well, the dots are just closer together. Okay, so there are different types of rate measurements. Almost all chemical equations have the same general shape when we graph out what a reactant's concentration looks like. Okay, so if I'm labeling my graph here, I'm going to use concentration on the y-axis, and I'm going to measure concentration with capital M, that's molarity. And on the right, I have time, which is usually measured in seconds, but can be any measurement. Almost always, a reactant is going to have this same general shape in its curve. And there are reasons for it being this shape. Okay, so I'm ready to show you the three major different types of measurements that you can make on a rate. So you can first find out how much the concentration is changing at the very beginning of your reaction. This is called the initial rate. The initial rate is special. The initial rate is going to tell you how much the reactants are going to react right when they start interacting with each other. The initial rate is almost always, like 99.999% of the time, almost always faster at the initial starting of your reaction than any other measurement. There's a reason for this. Okay, so I want you to imagine that we are all in this classroom together. There are 19 of you, there's one of me, that's 20 people. And we're all going to put blindfolds on so that we can't see anything. And what I'm going to do is we're going to take all the desks out, and I'm going to tell you, run at your fastest speed, and as soon as you collide with another person, you and that other person are going to step out into the hall. At the very beginning of this amazing race of us interacting in the classroom, at the very beginning there'll be 20 of us in here. After the first interaction between one of us and another person, we're going to lose 2 people. So that means there'll be more space in the container, there'll be more space in the classroom for all of us, but there'll be 2 less people. And then the next group of people will interact and they'll move. And so it'll take longer for a person who's left behind to interact with another molecule, another person in the classroom. And so you can think of the chemical reaction in the same way. At the beginning is when you have almost all reactants. And so it's a lot easier for them to find another reactant to collide with. Molecules can't react unless they're next to each other, and usually a collision has to take place. So, like my mom in the parking lot, the chances are good of a collision. So at the beginning of your reaction, excuse me, you have a greater chance of collisions. So I'm going to write that here in capital letters because this is an answer to one of your homework problems. And I like asking this question so much, I can probably guarantee it'll be on the test as well. Okay, so this is the initial rate. The initial rate is a kind of instantaneous rate, but I'm going to describe what other instantaneous rates would be. So you can find an instantaneous rate at any point along the curve, An instantaneous rate just means that, it means what it says. Okay, I didn't think I spelled it wrong. Instantaneous. My bad. It means that you're going to look at the rate for any instant. And so the only thing that's special about an instantaneous rate is you want to have the amount of time that you're using to measure the change in concentration. You want that to be as small as possible, because how long is an instant? Like a second or less. So you want this to just be a very fast measurement. So I'm just going to write that here. This is just a quick measurement. The initial rate is a type of instantaneous measurement. You just can only calculate the initial rate at the very beginning of the reaction. And then the last kind of rate, I'm just going to circle it down here on the bottom, is called the average rate. And what's special about the average rate is that your change in time equals the amount of time for the full duration of the reaction. The initial rate should always be faster than the average rate, because over here you can see that the graph kind of flatlines. It means that your concentration isn't changing very much, because you're getting so close to there not being any reactants left over. Okay, so now I want to show you what a curve would look like for products. If you need to pause to continue taking notes, do that. Oops. So I'm going to draw this again. Concentration is measured in molarity. Time we'll measure in seconds. And now let's take a look at what it should look like for a product. At the beginning of a reaction, how many products do you have? Before you start making sandwiches, how many sandwiches do you have? You should have none. Is that my hair? Oh, my Lanta. So we're going to start down at the bottom. And your curve should look basically the opposite of what your curve looked like for reactants. I don't like the way I drew this. Really, the amount of change that you have at the beginning, your slope should be greatest here at the beginning. I'm going to write that down here so that you can see what I mean. So at the beginning, your initial rate should again be the fastest. And that's because you have more reactants reacting. That means you also have more products that are being produced. And so then again, you can also find the average rate. You can find instantaneous rates like throughout. And that's all the same. So this is what it'll look like for your products. Something like this. All right, so let's take a look at the 3 different things that affect the rate of a reaction. The first thing is temperature. The higher the temperature, the faster the molecules are moving. And so if you think back to the example of all of the people with our blindfolds on, if we were at a higher temperature, we would be moving faster than we would be if we're moving slow at a lower temperature. So the higher the temp equals a greater rate. What does that word rate mean again? Its other word is speed. So that means that your reaction will occur faster at a higher temperature. the odds of us colliding are going to increase if we're all running at absolute top speed. The second thing that affects how fast or slow a reaction takes place is the surface area of the reactants. I'm going to write that on here. The greater the surface area, the faster the reaction. And the reason for that is simple. When you have an increased surface area, you are going to have more spaces available for collisions to take place. So a greater surface area would be like if we have all of the people still in the room, we've got our blindfolds on, but now we all have, like, you know, those inflatable balls that a person can go in? We are all wearing an inflatable ball. So our surface area is increased because the volume that we're taking up has increased, and so the likelihood of us like colliding with each other is going to be pretty high because we're all wearing these big bubble suits, and there'll be 20 of us in here, so we'll all be kind of like jam-packed. Another good example of increased surface area would be like if you have to melt butter. If you just put like your full stick of butter in your pan, it'll take a little bit of time. If you break it up into smaller pieces, if you cut it and then put it in the pan, it'll take a lot less because more pieces of the butter are touching the surface that is hot of the pan. That was janky. The third factor that affects reaction rate is the concentration of your reactants. These square brackets mean concentration. The greater the concentration of your reactants, the faster the rate of your reaction. So again, the classroom with all the 20 people in it, let's say we also take all the people from Mr. Dermis's room and put them all in here. It'd be a hot mess because there'd be so many people in here. And so we'd be increasing the concentration of reactants. The odds of us colliding and making a reaction are going to increase dramatically. So that means that we will be producing reactants at a faster pace. These are the three factors that affect reaction rates. Make a star on this in your notes because I'm pretty sure I'll ask you this question. This would be like a written question and not necessarily a math one on your test. Okay, so if you want to take a little break, go ahead and do that. Pause this show and come back. Okay, so now we are going to talk about how we can do some math. And so I'm going to call this title or section expressing the reaction rate. So expressing means how are we going to put what we were just saying with words into something that makes sense mathematically. All right, so bear with me for a minute because this is going to be a little bit crazy. Okay, so here's my pretend example of a reaction. And what I'm going to do is I'm going to start out by writing rate equals. We don't have a symbol to abbreviate rate, which I don't know, we're using all the letters of the alphabet otherwise, but here we are. So we're just going to use rate equals. And so remember how we calculated rate from the very beginning. We have change in concentration of our chemicals divided by change in time. Okay, that's nice. But what we know is that a rate has to be a positive number because a negative rate would mean that the reaction is going backwards, and that's not what we're saying. And so in order to account for the fact that the reactants are being used up, you're going to always put a negative sign in front of change in whatever the reactant is. This is nice, but it doesn't really describe exactly what's happening in my chemical reaction. So if I have a reaction where, let's say I'm going to make a club sandwich here, and so I need 3 pieces of bread, because you know in the club they've got like that bread in the middle. Let's use 2 pieces of cheese, and then let's use 4 strips of bacon. That's my bacon. And then we've got 1 club. Okay, so the rate has to be equal for every single component of the reaction. So in other words, the rate for A has to equal the rate for B, has to equal the rate for C, has to equal the rate for D. If that's true, how do we account for the fact that we need to use 3 pieces of, damn it, oh. Okay. We have to use 3 pieces of bread for every single piece of cheese that we, or for every 2 pieces of cheese. But then we need 4 pieces of bacon. So we're using twice as much bacon as cheese. The way that we are going to account for that is by putting the stoichiometric coefficient as a denominator in our rate expression. Okay, so if I was going to write the rate law for this pretend chemical equation, this is what it would look like. Rate equals, for reactants, always negative. So you can, well, I'm going to show you the way that I do it. Change in concentration of A, capital A, because that's the name of my reactant, divided by little a, stoichiometric coefficient, times change in time. B is also a reactant, so I'm going to need that negative sign. I will have change in concentration of B divided by lowercase b, stoichiometric coefficient, times delta T. And numerically, those 2 numbers should be the same. How do I know that? I put an equal sign in between them. So mathematically, that means that those numbers have to be the same. All right, so what about products? Well, are you using products up? No, you're not. You're making them. So no negative sign for the products. Change in concentration of C divided by little c times delta T. And then the same thing will be true for D. Now, my friends, this looks complicated, but every single one of these problems is exactly the same. Every single one of these problems is exactly the same. Okay, so what I want to do now is do some examples of this from your homework. And so you can find homework number 8 on the class website. So pull that out and look at it. Let us start with the first one. So this is homework number 8, number 1, part A. I'm just going to write the equation down because otherwise I won't know what to do. Okay, so this is a nice easy one. Only 1 reactant and 1 product. So how will you start? All of them are started the same way. Write rate equals, and you're like a third of the way there. Okay, so we only have 1 reactant. That's my O3, which is ozone. When I was in college, the research group that I worked with, like built drones. Like they were little airplanes, but they're like essentially the early drones to collect samples from the ozone layer to determine like what was the percent of gases in the ozone layer. It was really fascinating. Okay, so that's my only reactant. Here's a product. So no negative sign for the oxygen, but then we should have 3 times delta T as the denominator on this part of the reaction. Okay, good. I want you to pause it and give B a try before I reveal the answer to you so that you can see if you're getting the hang of this. If you're not, that's okay. I'll do a couple more with you. If you get this one correct, you can fast forward. Or, I mean, at least to the part where you see the answer. Okay, so how will we begin? Rate equals reactant, negative, that is not an abbreviation for Hall of Fame. Product, no negative. Product, no negative. And I'll do one more. Let's see. I just want to show, I'm not going to do E because you can do that. It's not any harder, there's just more of it. But whenever you see a substance with a charge, you must retain its charge. So if I see on here that you're using just I and not I minus, I will take points off. So that's just the caution there about that one from E. But let's see, which one should I do? Oh, they're all pretty easy. Let's do C since it's the next one. Oh, dang it. So, also a handy thing, I bounced all these for you, so you're welcome. NO divided by 2 times delta T. That's a reactant, so it has a negative. Is Br2 a reactant or a product? It is a reactant, so negative. And now this one won't have, oh, that's kind of ugly. This one won't have a number because the stoichiometric coefficient is 1. And so you don't need to, don't write the 1. We didn't write it here, so don't write it here. NOBR, is that a reactant or a product? It is a product. So make sure that there's no negative sign there, but that one will have a number in the denominator before delta T. All right, wonderful. Now, when you are working on this homework on page 2, you can actually solve this problem as well. Firstly, it asks you to prepare a graph from the data. So just like I did in my example some minutes ago, you can go back and look at that to see how you would make the graph. And then it also asks you to calculate the rate of change of B for each 10-second interval. So it looks to me that there are 4 10-second intervals, from 0 to 10, 10 to 20, 20 to 30, and 30 to 40. Okay, so if we need to calculate the rate for each of those intervals, I'll show you how to do that. Our reaction is A equals 2B. So the first thing you must do is write a rate equation for this chemical equation. So we're going to do what we just did. I almost was going to do something wrong there, but that definitely is a negative because A is a reactant. Now B is not, it's a product. And so your graph should look like the product curve, the yellow one. So no negative there. Delta B divided by 2 delta T. Okay, so now we need to calculate the rate for B. Notice how there's no information about A in this problem at all. So that must mean we don't need that. So I'm just going to take out the part of the equation that I need. And the reason I can do this is because I'm just saying that this is equal to this is equal to this. So I don't even need this to be part of my problem at all. Okay, so how do we calculate? Let's do the first interval, 0 to 10 seconds. How do we do this calculation? Well, go back and look at your notes. It should tell you final minus initial. So what is your final and what is your initial? Well, time is 0. I'm just going to copy down this data here from the table. 0, 3, 2, 6. Okay, so this is your initial, because it's the first of the 2 rows. And this is the data you're going to use for the final. Okay, so change in B means final minus initial. So I'm going to go to the concentration section. I'm going to do 0.326 minus 0.00 divided by 2 times the change in time, 10 minus 0. And that will give us a number. Rates cannot be negative. So if you get a negative number here, it means that you've done something wrong. All right, so 0.326 divided by 20, you should get 0.0163. That looks okay. What's my unit? Your unit's always going to be molarity per second. If you miss your unit, I will take points off. So that's the answer for the first of the rates. Now you can do that again for sections 10 to 20, 20 to 30, 30 to 40. Part B says, how is the rate of change of A related to the rate of change of B in each time interval? This is how it's related. All right, you can answer those questions on your own. If you need another break, I would take one now. And we're going to spend a little bit of time on the rate law. So, what we were just doing, rate equals negative delta A divided by little a. No. Hang on. Sorry. Oh. Oh, dang it. Okay, hang on. Sorry. Okay, let me just start over. Rate equals negative delta A divided by delta T, or A delta T. This is called rate with respect to change in concentration. Or we call it the rate expression. The next thing I'm going to teach you is about the rate law. They're not the same thing. So keep this in mind, but put it out of your mind for right now. The rate law is something else. So the rate law, if this is my pretend equation, the rate law is going to tell us how changing reactant concentrations is going to affect the overall rate of the equation. So this is how we find the rate law. Rate is equal to K times concentration of A to the M power times concentration of B to the N power. This is called the This is called the rate constant, and it has its own value for every chemical equation. And so the old man scientists who have their work published in the chemistry Bible, they have all calculated these rate constants for all the known equations. But now, what the heck are M and B, or M and N, I'm sorry. M and N are something special. They are called the reaction orders. And you'll notice that there's no M or N in this pretend chemical equation. They cannot be determined by stoichiometry. They can only be determined by experimentation. And so we know what they are for experimentation. We know what they are for most common chemical equations because of the old dude scientists who did all the work for us. Okay, so how do you know what those numbers are? You have to be told that in a problem. Okay, so let me just take a look here at that. Let's look at number 5 on your homework. So that's on the very last page. Number 5 says to write the rate equation for each of the following reactions. Find the overall reaction order for each reaction. Okay, so we again have that nice ozone-oxygen equation. And so to calculate the rate law now, we're going to do this. And then I'm going to read in the problem, it says this reaction is second order with respect to O3. That means that the little exponent here is represented there. Excuse me. So O2 must not appear in this rate law at all because we're not given any information about its reaction order. The overall rate, the overall reaction order is just the sum of all of the exponents. So there's only one exponent, it's 2, so 2 is the overall reaction order. Oops, this is A. For B, we have N2 plus H2 yields NH3. So it asks us to write the rate law. So I can set up like the basic parts of it because it has to look like this. But now I'm going to go back into my problem and read what my reaction order should be. It says it's first order with respect to H2. So this number should be a 1, but remember we don't write those ones. And then it's third order with respect to N2. So now how should we calculate our overall reaction order? You're going to add all the exponents together. What's 3 plus 1? 4. I will teach to you all of the information else that you need on this page. So skip number 4, please. And number 6. Yeah, and 7 and 8 as well. I'll teach you how to do those things when we get together the next day. So if you are watching this because of the snow day, God bless you. If you're watching this because you just weren't here, also God bless you. You should be able to manage all of the rest of this homework, except for a few on the last page. I highly recommend that you get started on that sooner rather than later, especially since this is all fresh in your memory. This homework is not due until next week. However, in class on Friday, whether we have a snow day on Wednesday or not, I will be giving you another new homework assignment because we're a little bit behind. And so if you leave this to the last minute, things will get very confused in your mind. So work on this. It won't take you very long at all. These problems are all the same. Good luck.